Welcome everyone to the webinar of Zero Swarm dedicated to architecture concepts. It's a pleasure having you all here, and I want to let you know that this session is going to be recorded, and you can find it later on also on the YouTube. It will be published. So today we are going to listen to the presentation of our dedicated partners, Pouria and Marius, and let me show you the agenda. So our webinar is going to last 1 hour. And we are going to start with a project overview for about 10 minutes, and then we will jump straight to the architecture concepts. The whole presentation will take around 40 minutes. And after all, you will have a good opportunity to ask the questions and to receive the answers to them. So meanwhile, you can already start asking your questions in the chat. I guess that you have this opportunity, and you can see it above on your screens, the access to the chat and the Q&A. So without a long introduction, I would like to hand over to our technical coordinator. Pouria, the floor is yours for the project overview. Thank you.
Thank you very much. So very good day, everyone. Let me just quickly share my screen. I hope you can see it. Okay. Yeah. So very good day, everyone. So I hope you are fine and doing well. It's a pleasure to have you here. My name is Pouria Sayyad Khodashenas, and I'm the project technical coordinator of Zero Swarm. And I'm here on behalf of Huawei Technology Sweden, which is the office of Huawei located in Stockholm, Sweden. Today, I'm going to do a quick overview of the project, but then, as mentioned before, we are going to spend more time on the architectural concept of the project, which, I mean, for us at least, it's a great achievement and a good takeaway out of the project. So just to give you a brief, let's say, intro about the project, you know the short name, Zero Swarm, but you can see here on the screen the full name. It was a project that has been founded under the call that you can see here, Twin Transition, and in particular the topic 0108. The Twin Transition basically promotes the digitalization of industry from one side, and from the other side, promoting the sustainability and Green Deal objectives in our industries. So it's a hand-to-hand, basically objective that these two goals should be equally treated, and this is what we are going to see today throughout our architecture and in the project throughout our trials and other activities. We're trying to showcase this. The budget of the project in total is around 10 million, in which around 8 million was funded by the Commission, and the rest is coming from our industrial partners and contributors. The project has started in June 2022, and it will finish hopefully around the end of this year. I mean, just stay tuned, because we might ask for a bit of extension. So maybe early 2025 would be the end of the project. The project coordinator is from CERT, a very respected, basically, research center in Greece, and they are doing a very good job in this project, and you can see the other information. So as I mentioned, basically from one side we are seeing the more automation, the more use of, let's say, machineries and robots in the industrial framework. They moved away from being only mechanical machines. They moved to systems that also includes electronics and logic. Therefore, they are called cyber-physical systems. So from one side, they are physical machineries, but from the other side, they have this brain and logic. And then the next step is to create a system out of this system, or a sort of Internet of Things, where these machineries can communicate between each other, can work together, can perform tasks that individually one machine alone cannot do, right? So this is the whole concept around these cyber-physical systems of system. At the same time, as I mentioned, there is a huge, let's say, interest to move to more sustainable production, therefore reducing the emission, reducing the pollution, reducing whatever that could be harmful to our environment, right? So how we can put this together and how we can make sure that the element of connectivity from one side can secure this cyber-physical system of system, and also by doing so we can achieve the objectives of sustainability. And that was the main question of this project that we tried to answer. So here you can see the partners of the project. The project is quite big. As you can see, we have like 27 partners already here. You can see that they are coming from various countries. So in particular, we have 9 countries of Europe already engaged in this project. As you can see, the geographical distribution of the countries is quite interesting, because we have countries from the north, we have the countries from the center of Europe, we have the countries from the south, from the east, from the west. So there is a big, let's say, collaboration ongoing from different sectors, from different backgrounds, and this project is quite has been actually a quite nice learning process for all of us coming from different backgrounds. So in a nutshell, the goal of the project is to shift the manufacturing sector of today to more green and digital manufacturing of tomorrow. But to do so, we need to follow some principles like security by design, data sovereignty by design, privacy by design, and there are some technical elements that we need to follow in a high level, let's say, manner. So we would like to use and promote those items that are open, so they are reusable for other outside of the project activity. We would like to promote this active information continuum. So we are not only talking about connecting the data, but also the intelligence that can be spread all over this from the shop floor to the management layer of the system, and also some other, let's say, consideration like following the standardization and human eco design to realize this green digital manufacturing. Of course, to do so, we are also considering some trials to showcase the developments of the project are really fulfilling what we are claiming. And here you can see the different trials of the project. The project is quite ambitious, so we have in total 10 trials. In order to organize them better, basically we decided to group them in geographical, basically, groups. So we have so-called North Node, which includes 4 trials. You can see the list here, so I would not spend so much time to explain all of them, but it includes basically 4 trials. We will see some of them here today in the architecture, but hopefully in the follow-up webinars of the project, you can get more information about our trials. Then we have the central node, which includes the 3 other trials, and there are south node, which includes other 3 set of trials. I mean, just by looking at the trials title, you can see that they are covering different, let's say, aspect of the future manufacturing, from the use of AGVs to the safety in the shop floor, to more sustainable, let's say, production, remote quality of quality control, so on and so forth. So it's a diverse set of, let's say, trials that the elements and items created by the project will cover, come together, work together in order to achieve the both goals of digitalization from one side and sustainability goals as mentioned before. So with this, let's move to more detailed explanation of our architecture. As I said, at least for me, it's a good achievement, because it managed to bring together different perspectives from various worlds that they need to work together in order to achieve the objectives of the project. So maybe I stop here and I hand over to Marius, so he can go more in detail on his presentation. So thank you very much.
Thank you, Katya. Thank you, Pouria, for this introduction. My name is Marius Stanica. I'm with ABB since several years, 17 years almost, various positions and countries, currently in a connectivity role with regards to architecture and for the ABB motion. Now, I would like to present you something which is what I called a harmonizing approach for industrial automation system and system of systems for the architecture. But why are we even doing that? So that's one of the points, because yeah, somebody may ask, but we have some architectures and so on. Why shouldn't we use what we have and so on? But we have existing standards today. We have, let's say, we are trying to talk in this world of Internet of Things and so on. We are trying to talk more and more the same language, or try to understand, to talk a language which we understand each other. Therefore, we tried to, in the time, to create standards and so on. So therefore, we have some kind of generic architectural models already standardized and presented in various specifications. But what we don't have necessarily, or we didn't have an official industrial automation mapping, that's something which this project tried to do, again, in order to make everybody understand, and I'll try to show several examples afterwards. Okay, so when we started with, as Pouria was just mentioning, with 27 companies, with having several backgrounds from several places, several interests. So we started hearing about artificial intelligence, of course, because this is everything what everybody talks today, even if this was present more or less since quite many years in our domains. But there is an architecture for that. Then there is an architecture at device level. There is an architecture which exists at the shop floor, there are architectures related to the clouds and to the cloud solutions and how those want to intercooperate. Then, of course, there are network architectures which are wired, but maybe also not wired. And then we are going into cellular system architectures or wireless architectures. But if it's cellular, then again, it needs some kind of concept of putting it together. Then we have various software running in a controller, which has its own architecture, which has an own function blocks architecture. And all of these were discussions at the beginning. So it was a little bit like the Babylon Tower, right? So having to try to understand, first of all, the user scenarios. So what do we want to do first? So you see some examples here on the right-hand side. Like controlling AMR localization, like optimizing productions, like training AI with information, or the deep learning system with information, connecting everything together, replacing the devices, using energy efficiency in order to go to support the device going on and off, and so forth. So all of that, with all of that in place, then the point was what can we do? How do we approach that? And then we tried to make it systematically. And we knew that there are at least some defined IoT domain generic requirements for various architectures and for various systems, but they were generic, so they are part of some specifications, which I will come back on it in a few moments. And that was one line of activity. You can see it in the above part, which generated some architectural models and has already some specified views about the architecture. We will see it in a moment. Okay, but that was not enough, because we are talking about industrial automation. We will have to learn also a little bit industrial automation, because that was also another point. What is industrial automation in such a great consortium? What are the needs for it, and how the various participants of the consortia can contribute to the results of the project? So therefore, we have some industrial automation requirements, which are maybe based on the IoT generic requirements, and that generated some architecture specific to industrial automation. And we created a mapping, which was based on the views generated from the, let's say, from the generic specifications. And then we had the project itself. We had several trials, and then we heard, okay, each trial has its own architecture. We want to do something on our own and so on. But the point was not just to create a collection of several projects. The point was to create, let's say, to break the silos between these kind of projects, to maybe reuse some kind of aspects. And therefore, we had to relate the business requirements existing in the trials and in the existing EU project Zero Swarm requirements to the rest of the requirements, to the generic industrial automation, and to the, in general, to the IoT generic requirements. And therefore, we arrive to these architectural models, which we see it on 3 layers also here: generic industrial automation and zero swarm related. And then from that, we started to generate and to create software. We started to generate systems. We started to generate the trials themselves. So that was at least the approach which we tried to cover exactly the point of the Babylon Tower which we had before. So try to organize ourselves in a little bit. Now, I was talking a little bit before on the IoT generic architectures, and there are some specifications. There is one which is called ISO IEC and IEEE, also 31 and 41, and describes several views. And let's start with the functional views. You can see here on the right-hand side quite a drawing showing a system, actually, which can be considered top-down or bottom-up. If we consider it a little bit top-down, we can see that there are, let's say, domains and there are capabilities, actually. And the domains are various. There are user domains. Somebody's using a user interface sitting next to a computer and monitoring something. But if he or she monitors something, needs some kind of operation capabilities and some management capabilities, management of data, management of devices. So therefore, we have operations and management domain. It might be that there is somebody else doing engineering. If that somebody else is doing engineering, it might be that there are he or she needs to have access to an application in the service domain. If somebody needs various monitoring capabilities only, then of course there is a need to do discovery, to do access to various devices and so on. But that's not enough. As we go down, we can see that we have a lot of sensing, identification, and actuation elements. Of course, like in everything, like even today, which you have some metal stations here around in the country, and then you are receiving data. You need to, let's say, sense the temperature, and then, let's say, maybe set up some temperature in a place to live or something like that. So this is just a simple example. Then of course you need some control services, and then you have various physical entities, because you really have something existing there at the system, and which is the first interface of the IoT system to the real process and to the real system. On the right hand side, what we can see various domains. So that is the set of services requiring the same administrative concepts. So that is, let's say, the connectivity. We see composition. We see functional safety. We see cybersecurity. We see high availability or resilience, and then various privacy and user access management. So this is one of the views, let's say, and this is generic. I would say it applies to many systems today. Some companies are applying it one-to-one. Some others are applying it in another form. We can see it in a moment. Okay, we have the system, but how to put it together? So if we see, and we need all these domains and capabilities, all these needs to communicate, needs to exchange data. For that, we need networks, and I put here the network keeps the system together. I think this is maybe the most important statement here, because without networks, you cannot rely on just devices sitting standalone somewhere and doing nothing. That you are in the 1980s or something like that. That we had, or maybe even before 70s or 60s, having some devices sitting there and somebody had to physically go to those devices and to interact by hand to those ones. That's not anymore like that. So you can see again all the domains which we had before in the discussion, and then now we have networks in between them, like a glue, exactly as you see, like exactly putting something together in a system. Again, it's starting to look a little bit like the Lego. Yeah, that's the model and that's the concept, and I think that this is a very good idea, the Lego itself, and we'll see it in a second further, because it's something which is repeatable. It's something which allows us to build a system, which builds a system from parts, and then from those parts we can build even a bigger system that is a system of systems. And these are part of the specifications, of course, the 3141. And of course, all these capabilities, what their communication needs are, they need to be fulfilled some quality of service. What is quality of service is you need to deliver something. You need to deliver something at a given moment or a given quantity or with a given delay. And this is exactly the model of quality of service which the IEEE is specifying, the bandwidth, latency, and deadline. So these are exactly the traffic types modeling which are expected to happen in such a system. And therefore, we try to build this complex model here with various control domain, data domain, access domain, and then security. And then we were discussing how can we manage to put together the cellular system in there and so forth. So that's where it's maybe looking a little bit dangerous, but let's look farther and see how this goes on. A step back first. So as mentioning before that we should think in a Lego model. You see here, I was trying to show one piece, but this is actually part of a specification. It's the ISO IEEE 3164, and you can see this is actually a repeatable model. So everything what we do today in our devices, be it that they are industrial automation, be it that they are in automotives, be it that they are in planes, be it that they are in wherever. In our intelligent devices today, you have several aspects. So first of all, if I'm starting, from below to up, they have a compute area. They have some kind of a capacity of executing logical actions, following their functionalities. They have a capacity to store some data. It's not possible to do just some logic without being able to do any storage. So that's something which is needed too. And they need to communicate. Again, we are in Anno Domini 2024, so we are not having to go to each and every device physically and connect to it manually and do something to it. So therefore, they have, let's say, even so, they need to have a communication mechanism for manual connection because we connect the computer to them usually. It's even before we were not having computers, so that was a really long time ago, but now we are in a different situation. So therefore we have a communication concept. So all the various functionalities which need to be present in the device, so that you have SSH, if you have IP stack, if you have I don't know, if you have some MEC layer capabilities like a clock synchronization stack, or quality of service supporting, mentioning quality of service supports, all that should find itself in this comms part. And then it's part of the connect. So the part of the connect is really the port. I mean, everything has a port, even the mug which you're drinking coffee from has a port, and so on. So it's pretty simple somehow. So the port can be physical, or the port can be somehow logical, and it can be a radio, like for example for the cellular communication, or it can be really a port like you have the RJ45 communication in if you have a UTP7 network or a fiber network. If you have, then you have a special port for that, and so on. So we will see that all these pieces repeat themselves actually in a bigger architecture. So all these pieces are let's say being put together, and this is, let's say, even a small part, let's say. So all this kind of these kind of elements are deployed, let's say, in sensors, in actuators, in controllers, in drives, in HVs, in robots, and so on. You will see in a moment some examples actually, and that forms what the specification 31 and 64 says, the layer of edge devices. And then, because we have quite many of such devices, we need to put them together somehow, and we need to kind of have an approach to gather data from them in a rigorous manner, so that we avoid, let's say, loss of time with the processing of data. We avoid lots of costs, because some of the cloud vendors, or many cloud vendors, actually have as a business model the volume of data being handled. So we need to do this kind of pre-processing, and we may need also do some pre-processing locally there, at the level of the installation somewhere. There is the data center level, which is, let's say, used very often for monitoring configuration aspects. This is something which is local, but then you might have even a centralized one. Imagine the following use case. And this is what we had, I remember when I was working in Italy, we had a great electricity vendor offering services, and they had a centralized control area, and they were able to control several power plants all over the country, right? So in this kind of case, we have like the level of the centralized data center. Yeah, that's, let's say, a generic architecture. So this is what we understood up till now. We understood that we had quite many requirements, scenarios. We approached them by a systematic way of handling at the various layers, generic, industrial automation, and the project. And then we looked on how can we see the various architectures, how various architectures can be put together. Why do we need to put them together? Why do we need to make them exchange data? What's the importance of all that? And we gave already some examples. I was talking about the electricity installation, what power plants, what I was discussing before. That's also important because there are quite many costs in handling them. So if there are issues, then there are quite big impacts at the level of the cost and the level of the customers. Okay, but how to do it in industrial automation? So industrial automation, long years, worked also in a layered way. So basically, if I'm starting from the lower layer, following the specification IEC 62264, so that is the ISA 95. This is a very, very classic part of the industrial automation, where you see three level, in the lower part is three layers here, and they are, let's say, the actual production process. Then you have some sensors to that, and then you have the supervisory control. Basically, what it was done before, and industrial automation, still many installations are working like that today, no doubts about it, and that's very good that they do. There were, let's say, the process itself, then there are some sensors gathering data. Those sensors are sending data towards some I/O devices. The I/O devices are already gathering something and aggregating some data, and they are sending to the controllers. The controllers have some logic. These are, let's say, the what you see here, the supervisory control of the production process. And then they send some data back to some actuator so that they control the process. So therefore, you have various types of controls here. You have continuous control, which is, let's say, something which is based on a temporal execution, and then you have discrete control, which is something which is very often based on events, and then you have some batch control. So these are various types of control, classical control mechanisms in industrial automation. And you see here the time frames for that is milliseconds, I would say, microseconds, seconds, maybe hours and minutes. You can do that too. You can have something at this point. Now, these layers that before, they were not connected directly with the other ones. So they are connected with just the above layer, which was the manufacturing operation management, which basically trying to steer the process in some way. And then, of course, you see that the time frames are totally different here. The cycle times are different. The reaction times are different. You see that we are talking about days, shifts, hours, and so on. So this is already a higher level. Even a higher level on that was how to handle the inventory, how to handle the maintenance, how to handle the production, use, and delivery, and so on. So that there we were going in the business planning and logistics. Here, obviously, timeframes are even higher. So as much as you go higher in the hierarchy, the times are higher. There is a strong separation of concerns here. And the exchanges, as you see, they are just between the various levels, not between level 1 or level 4 or something like that. Well, this paradigm changed, actually, and it changed with the advent of the industrial Internet of Things, with the advent of bringing software, with the advent of higher capabilities of processing of devices, the lower costs of processing actually, and processors. So therefore, we arrived to actually go and define something which was called Industry 4.0. Industry 4.0 relates again to the automation pyramid, and the automation pyramid is something which was defined by the specification that I showed before, and you see it here in the drawing. It's exactly the levels as we were discussing before, but these layers, they are now just a part of it. So it's just one of the dimensions. Now we have another one, and those are on the left-hand side, the life cycle ones, and there are new specifications, and these new specifications, putting everything together, it creates a sort of a cube. So it's not anymore just let's say two-dimensional representation, it's a cube. So everything here can communicate to everything. So basically, I can communicate from the business to the product to the field device, or from the information level to the enterprise, or to the work centers, and so on, or to the data center. So I can do whatever today. It's somehow bringing internet in some way in industrial automation, and that is a paradigm change. And therefore, we need to still be able to steer that and to ensure security and to ensure safety and to ensure maintainability of that and tracing of faults and so on. So all that has to be considered. And therefore, we have to go one step further and consider our approach, but our approach on how do we implement all those models which we have discussed before in the IoT world into the industrial automation. And there we came up with some kind of an architecture model or architectural conceptual model where we are having a sort of an industrial automation application layer where it's something related to the sort of the data center, the functions defined earlier in the slides before. Then the connectivity layer, remember the network views and everything connecting, keeping the system together. Then the security, remember that we are opening the systems now much more. And anyway, security by obscurity doesn't help. And then we have all sorts of capabilities, and which are somehow shared between all these layers. Some of the capabilities are happening at the data center because we can do supervision, we can do management, we can handle digital twins, we can do offline representation of the system and then deploy it online before going, let's say, into production. We can do simulations, we can do a lot of other things. Nevertheless, we have to be able to go online and to collect the data. So we have a data aggregation and processing layer where we have various aggregations, as you can see here, and I was giving examples on the AI and OPC UA, but there are many others. Then we have, let's say, a connectivity layer. The connectivity layer is very, very important because it's the one putting everything together, and it's everything, let's say, which allows us to support eco design also. So not only at the level of a device, I may have to go out to power save, but if a device disappears from the network and it comes in, that has to be handled and has to be handled in a secure way, because without security, it can be that an attacker is simulating a device going out in power save mode and plugging in his device or her device in place. And then, of course, we need to have the discussion on the ports and the interfaces and their capabilities. So therefore, we had to go and to approach the model this way. But how to handle that? How to put these things together? So we were talking about the Lego pieces. So, and I will go on in a second to that, to some more examples. So once you have defined the domains, the capabilities, and then you created your edge entity concepts, what you show some slides ago in that model, which contain connect, comms, storage, and on compute layers, you need to think what you have in each of them. And that's kind of a few words here. And just cutting out the few words, let's cross to the real thing. Let's see that we have, let's say, for example, a PLC or a controller. And in this controller, we have some kind of a compute layer where you can find, and I give some examples here. Please don't believe that this is mandatory to have always an OPC server, an OPC client. That's something which is modern, and we want to go into this direction. And you'll see also an example or a potential example of how this can work in reality. But that's let's say next to something else, you may have existing field buses. Field buses is something which allows you to exchange data between systems in older manners or in legacy manners, which are still ongoing, and they are still functional, and they are, let's say, still may run in parallel to OPC-UA. Currently, OPC-UA is being developed, so OPC-UA is not so developed, but now we are developing it to the field level. Before, those field buses were covering exactly that field level. So most of our projects, so they run on field buses because this is something which is currently fully defined. Yeah, we have a runtime, which can be on one of these two elements, and then we have let's say programs and tasks, because the controller has to have some programs, has to have some tasks for those execution of data. Now there is an access management, there is security. So all the black parts here is some security examples. Not everybody can access everything. Not everybody should access everything. There is a user management. There is lots of other aspects. There is storage, key storage, and so on, security certificates and keys and so on, and then private keys. We can do various other configurations. We can aggregate data coming from the fields. This is the existing model. Remember the ISA 95 model, the Industry 3.0, which I showed some slides ago. We can handle alarms and events, because this is the role of a PLC. And we need to communicate further, but then it's again security, maybe at the level of the MAC or the level of the IP, but maybe we support discovery, maybe we support clock synchronization, we have probably an IP stack, and we have, or we may have a network configuration concept like the modern one. I was trying to use the modern one, the netconf, but it might be that there are some others like SNMP or some other models defined by some vendors on a proprietary manner. And of course, you have the connect part. So this is, let's say, exemplifying you how this kind of works. I did not put all the links and all the connections here because it will be, all these things are connected and exchanging data together. Following this scenario, following the use case. Okay, let's go a little bit farther. So if I put some notations, you will be able to look on those notations actually later on to see what they are. But I want to go on and explain this kind of complex system. So yeah, again, those layers which you already have seen. So you see the PLCs, you have a number of PLCs, you have a number of drives, you have a number of AGVs, yeah? And then in between them, there we have the connectivity, the infrastructure to connect them together. We have some gateway level, or let's say an aggregation layer, and we have the data center or the industrial automation layer, which we are bringing various elements together, and we have various parts of the system together. Now, let me start with the left-hand side, or maybe even we start with the upper part. So, and in the upper part of the data center, there is some kind of an engineer which wants to configure something, wants to look to some kind of data existing in a process somewhere, and he needs access to that. But how? Because that engineer may sit in that location X, and then the plant is somewhere far away, and hundreds of kilometers, or maybe several kilometers, just depending on the situation. And that's something what he has to be able to do. But therefore, he connects to the various gateways. So connecting to the gateways specific to those locations, those gateways are connected over the connectivity infrastructure, which can be cellular, it can be wired, it can be varying in various ways, let's say, but it has to be managed too. So therefore, we have several aspects here concerning quality of service, discovery, wired devices, non-wired devices, and so on. And then we have the devices themselves. For the PLCs, which have just seen the model, Drives are working in the same way. So here I'm trying the drive is something which controls the motor. So imagine that you have several motors being running there, and there are, let's say, a drive which connects to the power grid, and then which is, let's say, like a sort of an input converter or a rectifier, and then we can have several inverters following that one. So maybe a crane is being moving there, so, or several cranes are being moving there, and therefore we have several, again, the same kind of layers of communications, because all those elements need to exchange data, need to process data, need to represent data. Why? Because the engineer, the operator, the supervisor is interested on that data and needs to do something with that. So all these devices are producing data. You see, then we have also an AGV, which is not so far maybe from the PLC in the architecture. Yeah, this is maybe an example here, just, but they can be even together. So it might be that in an AGV we have also a PLC. We have some backup slides for that. Just a second. Yeah, some backup slide for that, and then we can look onto that too if you want. The AGV movement, the automatic guided vehicle movement, is steered by a PLC. So there are also drives there which are controlling the wheels on how it moves and so on. Then there is an AGV. In the AGV, there are capabilities to avoid obstacles, to do location, and so forth and so forth. I even didn't put all that in the compute part. I just put here to make it simpler, just the OPC server with its own information model to just show the world what is happening there, because the world is somewhere out here, you don't even see it, but it's connected to the data center, it's connected in that way, so it needs the information. And then we have the various aggregations, and you see here already some kind of processing being done at the gateway level, and then further on some further processing happening at the cloud level. So there are, for example, machine learning algorithms running there, deep learning algorithms, maybe even language models. Somebody can create some kind of a query in the future running and saying, please tell me what I have to do in order to avoid that my motors are getting into a break soon. So what kind of actions, corrective actions can I do? So these are some kind of things which we try to support, and you will see some examples coming in further on in the trials. So yeah, that's, let's say, the overall model. Maybe it's a little bit complex here, trying to do some data exchanges. I'm always open to further discussions here, and of course I didn't want to put everything because that's much more than that. But yeah, it's at least to try to show you that there are some sort of a complexity in the simplicity. So you have to be able to look simple to the things, but in order to do an architecture and in order to do a harmonized architecture, you need to understand it completely. Good. So how do we deploy it? We deployed it in the following way. So for example, you see here in one of our work packages, there is exactly the same kind of model put into the different way. We have some kind of a processing at the lower layer. We have, let's say, you see it here in this model that you have some kind of AI working in some nodes, in some others you don't have, and then these nodes are communicating and sending data somehow out, as we just showed before. And we have, let's say, a computing layer. It's a sort of an adaptation layer, which is connecting to the data in various ways. And then there's trying to do metering of the network, is trying to monitor, and then it's trying to acquire data effectively, either in this example over OPC or either over MQTT for simpler devices. And then, of course, the adaptation layer, then some configuration for that, and then we have again some kind of communication with the centralized or distributed data center, where we have some further services, and then we have some other level in the cloud. So you see there are all sorts of processing following the layer, because we need to optimize very much the way we're processing data due to the, again, quality of service, costs, maintainability, deployability, and so forth. And therefore, this kind of separations between domains and capabilities at the various levels. It can go even more complex than that. So we can have, let's say, as you can see the model, what we showed before. So something changing and moving exactly to this platform. This is one of our esteemed partners at Repack. So this is the production line, and therefore we have several elements there too. So in this case, it was the AMRs or the AGVs, the autonomous moving robots or the autonomous guided vehicles. They have, you can see them here. Some of them, what the use case was here with food processing and food packing. So therefore, some of them, they have, let's say, some kind of packets, some packets which can handle the applying a film over some boxes of food, and some of the MRs have some kind of the food itself, and then the robot which is packing, and this is packing the food by itself and then moving it to other production areas. Then we have some sealer, some sealer for those packets or trays, let's say. Then we have again some cobots which are trying to move the packets farther on. We have a quality control camera, and then we have some edge capabilities, either from the Schneider Electric side, either from the Renext in this case, and we may even have digital twin representations. This is, let's say, the overall view. But if I'm looking exactly to the aspects of the implementation. So if I'm looking to how exactly those pieces, those Lego parts are implemented, we can see it here that we have a runtime in the controllers. We can have even hardware acceleration in there. It goes into very many details on how to implement the learning algorithms and so forth. So that's, let's say, an overall deployment perspective. And there, this is, you can see here the box which is actually supporting this logic, and which is going to be deployed there. We have OPC-UA here too, very better in exchange of data. OPC-UA is a topic per se. This is not in the scope today. We'll probably plan to do another seminar or another webinar on that in the coming time. We have several models, and we have maybe one model we are trying to make a harmonized information model there too, but that's a presentation per se, and that's a discussion per se, because the way you represent data, the way you create your system is clear, and you have a clear notion of how to put those little pieces together. Unfortunately, these systems are a little bit more than the Lego pieces. They have intelligence on their own. So that intelligence is data, and data has to be represented in a given way. And that would be very useful to be represented in a harmonized way too, because otherwise we end up into various mechanisms, and we need to make a huge effort to map things together. And that would be very nice to be avoided. Yeah, so that's something which is going to come, and yeah, that's kind of it. So I wanted to just to show you a little bit now, a small example. Actually, again, this is an AGV, a complex AGV, which has a PLC, which has an AGV, which has an agent for handling the location. The PLC is handling the movement and helping the equipment to move, and you see again the various kind of aspects being implemented there. And with that, I would like to hand over again and stop sharing maybe, and thank you very much. And I'm looking forward to your questions.
Thank you very much for the presentation. And indeed, I would like to ask whether we have some questions from the audience. You can just raise your hand and I will open the microphone for you. And indeed, if you don't find it convenient to ask the question, you can always drop it in the chat. Let's give it another minute here, if maybe it's cooking the right question. Yes, we do have one from Estella. Let me open your mic. So please go ahead.
Hi, thank you for the presentation, Pouria and Marius. It has been really interesting. I'm curious about the very last slide that you presented with the AGVs. And I saw there a few layers where you do some edge processing, cloud processing, etc. So I'm kind of interested on the processing that you do at both the edge and the data center or the cloud. I'm seeing a lot of artificial intelligence there, I believe, or and also application management, supervision, etc. So if you could shed some light on this, please.
Yes, of course. So there is some kind. So let's say first of all, the device needs to move and do its own role actually. And you saw the repack model, so it has to avoid collisions, it has to avoid other AGVs, it has to avoid people, it has to connect with the robot and so forth. Now, I would like to, for example, make sure that I'm not having, if I give you an example of a processing of the data related to condition monitoring, I would like to see the condition monitoring of the, I don't know, or the either of some motors or the AGV level, or the wheels or something like that. So maybe I have some vibration sensors and I have some vibration data, which I am able to produce it and then send it over the OPC-UA server farther on to the gateway. And in the gateway, I can do some pre-processing. If I have several and I have a fleet of AGVs, then I should do that instead of sending everything straight to the cloud. And then I do that kind of processing and a level of each gateway, taking care of a number of devices, then sending and grouping the information to the cloud. And there I can have that further information, and I can, for example, look and understand, okay, I have some kind of a vibration at AGV 1 and 252. I have to take some measurements. So then I decide from my client, from my OPC-UA client, going over the gateway, and then again to the AGV, tell it, okay, stop, please, get into maintenance mode. Into that, I need to make sure that my network doesn't crash or some kind of a huge alarm system come into that, and I have to take care about that information. And I have to say, okay, good, now this is in maintenance, we have to go there, so I have to send the information to some teams, or maybe even we have let's say at this kind of a data center, we can create automatically a ticket in the IS system, in the IS group, which goes there and fixes or the robotic group, which fixes the wheels or something in the AGV. Then the AGV is signed out as okay again and functional. So this is one example. This is one scenario. So you can imagine various other scenarios. I hope I answered your question.
Yes, thank you. Very interesting. Thank you very much.
Maybe I can just interrupt a bit here. So maybe Marius, just some follow-up on the same question that Estella asked, basically. So if you look at this scenario of AMRs and AGVs that you represented basically through this harmonized architecture, that clearly shows that there is a storage, there is a COM part, there is a connector, basically there is a connection, and each of these single AGVs either being a single unit or a swarm fleet of AGVs, basically. How much do you see the need for a real-time communication from one side, offloading of intelligence from the AGV or this ARM system on the edge, and the necessity of doing a kind of layered, basically decision-making or intelligent decision-making from the edge all to data center and vice versa? I don't know if my question is clear.
Yeah, your question is complex, I would say.
Exactly.
So first of all, let's
start. Maybe just to put it
together.
simple.
No, I got it. Let's piece it together, maybe.
Yeah.
First of all, you asked about real-time communication. For me, I avoid these terms because I, in general, prefer to use soft real-time or isochronous real-time. Isochronous real-time is something which means you have a deadline of microseconds, either that your information reaches one point to the other point. That means this is not for humans. That means this is for moving something or processing something very precisely, doing motion control, doing coordinated motion. Coordinated motion is needed. For example, when you want to have several robots working there, or you want to have people collaborating with those robots, so cobots, so not to make sure that Those cobbles do not injure people, so that can happen. And there you need to have isochronous communication. Yeah. If you want, for example, to just move a crane slowly and so on, that's already not anymore isochronous communication. That's something which is maybe real time. You have to make sure that the crane doesn't fall, so you don't get into a harmonic oscillation when you move the crane and the crane starts moving and it falls down. So there are other elements which you need to consider. Other elements then goes to the second part of your question. Where do you handle that? You handle it at the level of the drive, you handle it at the level of PLC, or you handle it in the let's say in the edge. In general, in the edge, you don't handle that information, that kind of information for swaying, anti-swaying, or something like that. It's called for the cranes and so on. You handle it at the drive level or at the PLC level. At the level of the edge, you want to make sure that you're handling and you're processing much more data, which is coming, and this is more conditioned data. So vibrations, strange vibrations. You are evaluating sensor information there and see, hey, that's strange. It looks strange. It's like a heartbeat or something like that. Your heart beats badly. So what's wrong here? It's like doing, let's say, a sort of an a small electrocardiogram here at for the for the crane, let's say, at the level of the edge and so on. So you're trying to look and say, hey, there are some cranes here which look bad. So please, at the level of the cloud, process me this information. That kind of processing, it's not microseconds, it's not milliseconds, it can be hours, it can be days. So, did I answer your question?
Yeah, absolutely. Thank you very much. And it's just like to emphasize the fact that although these pictures seem to be a bit basically maybe in the first look complex, but it's again a good way to show that after all, we're talking about like a nerve system that, like, or in your body, some of the reactions are done exactly in the point. Some of the reactions are done probably through our brain, which is maybe far from our hand that is touching a hot spot. And I think the example of the crane basically very well reflects this complexity within this context. So yeah, sorry to interrupt. I don't know if the others have questions, please.
No, not so far, so you can. So if there are no more questions, yes, that's we can wrap it up. Unless you, Pouria, want to comment on some other matters.
No, I just wanted to thank you both. I mean, yeah, and our audience for being here, please.
Yeah, thank you very much also from my side.
Great, then let me quickly remind you on the way to connect with the project and to stay tuned. So you have several options, and the first one is, of course, to become part of our community. So you can register and follow us there. Another option, of course, is to visit our website and to see all the updates also in there. And the vibrant place to find the latest news about the project is, of course, the LinkedIn. So feel free always to connect with us, to reach out to our experts and to ask questions, give feedback, or suggest some things. That will be always welcome. And indeed, I would like also to express gratitude from the project for joining today and staying with us. I hope that you found it interesting and useful, this information, and don't miss out our next webinars. Thank you very much for your day and have a wonderful rest of the week.
Thank you very much, Pouria.
Thank you very much,
Katarina, for organizing that, and everybody. Thank you.
Thank you.
Huge pleasure. Goodbye.
Bye-bye.